Hey everyone, and thanks for joining me. I'm Sergio Pedri, and I'm a software engineer here at Microsoft. I work in the Microsoft Store client team, and I also lead the .NET Community Toolkit. Now, today I would actually like to talk to you about something different, and specifically, I would like to introduce you to ComputeSharp, which is a project that I've been working on for the past few years. Now, I will go over what the library is and what it can actually do. I will briefly touch upon how it leverages the power of both DirectX 12 compute shaders and Direct2D pixel shaders on Windows to accelerate workloads and perform image processing and computations. And I will also show examples of how and where it's currently being used in production. And finally, I will also show you how you can use it to augment your own native Windows applications. So first, what is ComputeSharp? So in a nutshell, ComputeSharp is a .NET library that lets you run C# code on the GPU. And it does so through multiple different backends that you can choose from and mix as needed. So as I mentioned, you can use either DirectX 12 compute shaders or D2D1 pixel shaders. And it does all of this without you needing to ever touch any native code yourself or system API, and all while just using C# code with the same tooling that you're familiar with, including IntelliSense. So this also means that you never have to write HLSL code yourself, where HLSL is the shader programming language for DirectX. So you just write C# for all of your shaders, and then you let ComputeSharp do all the rest of the work for you. And so since a picture is worth 1,000 words, or in this case, a video, I guess, let me show you a concrete example of what you can actually do with ComputeSharp. So what you're looking at here is the UWP sample app for ComputeSharp, which is also available in the Microsoft Store. Now, this app showcases several pixel shaders that I've ported from GLSL, which is the shader programming language for WebGL, over to C#, and that are running using ComputeSharp and its UWP swap chain panel Xaml control. So this means that all of these shaders that you're seeing here are running in real time using shaders that are entirely written in C#, and with ComputeSharp taking care of everything from creating DirectX 12 devices, setting up textures, resources, command lists, and managing the entire render pipeline as a whole from start to finish. Now, you might be wondering, what does a pixel shader actually look like when written with ComputeSharp? And so let's look at one together. So this is the simplest shader that I could think of. And in this case, it just shows an animated color gradient that changes over time. So let's call this the Hello World shader. Now you can see how the whole shader is simply a C# type, it's a struct. And in this case, it's capturing some values. So there's this float time value that's used to tell the GPU about the time that has passed so it can calculate an animation. And then you can see in the shader body, we're doing some computation to calculate the final color to display at any given pixel in the output. Now, if you're familiar with HLSL, you might also recognize some types and APIs here. So for instance, there's the float2 and float3 vector types. And then there's also some HLSL intrinsic APIs, such as this cosine method being invoked. Now, this is because ComputeSharp ships with a full set of projections for HLSL, which means that it lets you use the same types and APIs in C# as you would in HLSL. And there's actually thousands of them, and they're all available. Now, this gives you two main advantages. So first, especially if you've never used HLSL before, you never have to worry about actually learning how to use it. You just write C# and ComputeSharp does the rest. And second, this also means that you can benefit from the great tooling that C# offers, including IntelliSense suggestions for all these intrinsics. Now, here on the right, you can see what the same shader actually look like after being transpiled to HLSL. And so what ComputeSharp does is it transpiles your C# shaders to HLSL at compile time using a source generator and a Roslyn syntax rewriter. And it can also even precompile these shaders for you. This means that you don't ever have to worry about bundling the DirectX shader compiler, nor to manually embed the shader bytecode into your assembly. And you can also see here how ComputeSharp is taking care of doing some additional transformations. So for instance, you might see that there's a constant buffer now here that is used to marshal all the values captured by the shader onto the GPU. We now also have a 2D texture, which is the one that's used to write the output values to. And we also have some automatic bounds checks that are used so that we make sure that we only ever write to the target dispatch area in the output. So this is just an example of how ComputeSharp lets you not have to worry about all of these HLSL specific implementation details. So you just write C# and it does the rest. Now, let me show you an example of where ComputeSharp is currently being used in production and how it's helping in a real-world application. So I've been working with Rick Brewster, who is the developer of Paint.net, to build a new D2D support for ComputeSharp, which is now being used in Paint.net both internally and for plugins. So Rick has rewritten almost all of the effects in Paint.net to be D2D pixel shaders through ComputeSharp, meaning that it could write all of these effects entirely in C#, while at the same time also getting the GPU acceleration that these pixel shaders provide. And we also enable support for this for plugins, meaning that you can now write your own custom GPU effects in Paint.net using ComputeSharp to author the D2D pixel shaders, and everything just works nicely together. So here in this screenshot, you might see this bokeh blur effect that's the effect that I adopted from the version that Professor Mike Pons wrote, originally in Python. You might know him or recognize the effect if you're familiar with the Computer File channel on YouTube. And I've migrated that version from Python over to be a D2D pixel shader using ComputeSharp. And you can see that being now rendering live in Paint.net. And to also give you a sense of the performance difference, here's some benchmarks showing the bokeh blur effect and Gaussian blur effect running either on the CPU using ImageSharp or on the GPU using ComputeSharp. Now, you will notice that the GPU version is about 17 times faster on my machine, which has a Ryzen 2700X and a GTX 1080. And this just shows you the kind of power that using the GPU can unlock, which can now access with ease entirely in C# using ComputeSharp. And to be clear, this is not saying that ImageSharp is slow. In fact, it's not, and it's extremely efficient. It's just that the GPUs are really well suited for this kind of heavily parallel workloads. Now, I want to actually give you an overview of the entire pipeline that ComputeSharp has that allows you to just write these shaders and have them run seamlessly on the GPU. So of course, the starting point is you just have to write your own C# shader. So let's look at another one together. In this case, I will pick a slightly more complicated one. And this shader is actually a part of the bokeh blur effect that you saw earlier. This is just meant to show you some of the more advanced features that you can also use. So in this shader, we can see that we are capturing a couple of values. We're now also accessing several resources on the GPU. So specifically, we have 3 2D textures, and we also have a read-only buffer. You can also see how we are capturing some values that use a custom user-defined struct type. So we can see this complex 64 and this complex vector 4 types. And then once again, we can see some HLSL projections. So we have this float4 vector type, some HLSL intrinsics APIs. So that would be that clamp method being invoked. And we can also see some custom user-defined operators and some instance methods. Now, the details are not really important here. The point here is just that you can see how you can write normal-looking C# code and then rely on ComputeSharp on doing all the necessary transformations to run all of this code seamlessly on the GPU. Now, from here, this is where the source generators in ComputeSharp actually kicks in. And what they do is they will generate several methods that are needed to support the execution of these shaders. So let's quickly go through them. So the first one is called getDispatchID. Now, the point of this method is that it creates a semi-unique ID for each shader that's used internally in ComputeSharp to handle caching for all the various pipeline objects. Now, you can see that in this case, this method is extremely simple. And that's because this particular shader will always be the same every single time you run it. That's because this shader is not relying on something that's called metaprogramming. So to explain what that is, imagine you wanted to have a shader that applied a given transformation function to all values in a given texture. So for instance, the first time you want to run that and add 1 to all values, and another time you want to multiply all values by 2, and so on. Now, you wouldn't want to just rewrite a different version of the same shader just to change one line of code. And so what ComputeSharp allows you to do is to just have a single version of your shader and then capture a delegate. So it could be a function that takes a float and returns a float, for instance. And then it will just dynamically combine these various bits to create new shaders at runtime, which you can then invoke. And so this method is part of the infrastructure that's needed to support this. Next, we have load dispatch data. And this is the method that's responsible for extracting all of the values from your shader instance and marshalling them over to the GPU. So you can see that there's 2 parts to this. So the first is we are reading all of the values that will go into the constant buffer. So in this case, we have those 2 float fields. And you can also see how ComputeSharp is taking care of respecting the padding rules that the DirectX runtime requires for the constant buffer. That's all handled automatically. And next, the second part is we are also extracting the GPU descriptor handles for all the various resources. So we have 4 here. And this is needed so that the runtime can then bind the various resources that we want to access onto the shader so it can read and write to the correct memory locations. Next, we have load dispatch metadata, which is responsible for extracting all of the high-level information on a given shader that's used internally by ComputeSharp to create what's called a root signature, which is an object used by the DX12 runtime to prepare a pipeline that's used to execute a shader. And so you can see here how this will prepare all of the info about, for instance, the various resources that this shader has. And it also includes information about what kind of resources they are, whether they can be read to, written to, what type of elements they contain, and so on. Next, we have build HLSL source, which you can see here. And this is where the transpiled HLSL source for each shader is actually stored. Now, there's actually 2 reasons to have this. So if you are not precompiling your shaders, this is what allows you to retrieve this code dynamically at runtime and then compile shaders on the fly. But then even if you are precompiling your shaders, it's still useful to have this code available at runtime so that you might, for instance, introspect into a shader to check what actual HLSL code was being used so that you can make sure that this shader is doing exactly what you want it to do. And so this method is available so that you can do both things depending on your needs. And then lastly, we have try get bytecode. And this is what actually allows ComputeSharp to extract the bytecode that will then be executed on the GPU. Now you can see here that in this case, we have opted into precompiling the shaders. And so ComputeSharp has done that at build time, and it has now embedded the entire shader bytecode into this method. So we can then just load it directly and then execute it. And this is what the sample app is doing, for instance. So this allows application to have the best possible startup performance because there's no time wasted just compiling shaders. Now, this is entirely optional. And so if this hadn't been the case, then we would have also had a fallback path here, automatically invoking the DirectX shader compiler to get the bytecode at runtime. Now, this is just to give you a general idea of the kind of work that ComputeSharp is doing for you behind the scenes automatically so that you don't have to worry about any of this. And another advantage of using source generators for all of this is that there's no reflection being used, meaning that all of this can also work in AOT scenarios, including native AOT, even in reflection-free mode. In fact, I have a version of the sample app that's running entirely on Win2D, on Win32 using .NET 7 native AOT, and the whole thing is just 2 megabytes in size. Now, you might be wondering what the code actually using ComputeSharp looks like to run something on the GPU from start to finish. And so I want to show you a couple of end-to-end examples of some work being done on the GPU. Now, ComputeSharp offers 2 different modes of submitting work to the GPU. So let's start from the simplest one, which we'll call eager execution. Now, in this mode, you just submit commands to the GPU one by one, and then proceed after each unit of work has completed. And this mode is perfect if you're just getting started with the library, if you just want to try things out, or if you just want to submit some very small and self-contained units of work to the GPU. And so in this example, you can see we have a very small shader that's just taking a buffer and then multiplying all values by 2. And then we are first allocating an array with just some random numbers. Then we are allocating a buffer on the GPU and copying the values from this array. Then we are dispatching the shader onto the GPU, targeting this buffer that we just allocated. And then finally, once that's done, we are copying back the values from this array onto RAM so that we can read them from the GPU. And that's basically it. So with just 3 lines of code and a very small shader, we now have some C# code running on the GPU with ComputeSharp doing all the rest. Now, what if you wanted to run a more complicated sequence of operations though, and you also wanted the best performance possible? And so for this, ComputeSharp also offers a computational graph mode. And this mode basically lets you prepare a sequence of operations and then submit them to the GPU all at once as a single batch. And this greatly reduces the overhead when dispatching work from the CPU side. And it also allows the GPU to leverage what's called async compute, meaning that it can run multiple shaders simultaneously, and this maximizes GPU occupancy. Effectively, it gives you better performance whenever possible. And so if you look at this to see what it actually looks like in practice, first, we are creating this compute context object, which is the API that ComputeSharp offers to actually queue all of these operations. Then we are preparing our custom computational graph. So in this example, we are logging some messages, which will use the DirectX Pix library behind the scenes. Then we are dispatching some shaders. We are managing some resource barriers to synchronize access to shared resources across different shaders. And then we are basically free to build our fully customizable computational graph. And then the second we go out of this scope and the compute context gets disposed, then all of this work will just be queued to the GPU all at once. And then you can see here how we're also using this await using statement, meaning that we'll be able to asynchronously await for all this work to be completed instead of blocking the caller thread. Now, you might also ask, what about Xaml support? So I mentioned how the UWP sample app is using ComputeSharp to render all of those shaders via the swap chain panel Xaml control. And so let's look at what that actually looks like in practice. So in this example, you can see the Hello World shader from earlier. So this is what the animated color gradient I mentioned actually looks like when running in a real app. And so all you need to do to get something like this working is basically there's two steps to this. So the first is you need to use the computer shader panel XAML control, which you can just place in your XAML page or control. And then you can just assign a shader runner object to this panel. And this object will tell the panel how to render each frame. Now, in this case, since it's a very simple example, we're just telling it to render our shader for each frame. But from here, you can build your fully custom render graph to display anything you want on this panel. So it's fully customizable. And you can also see how it really just takes one single line of XAML and one line of code behind. And just like that, plus a small shader, you now have a live animated wallpaper running using DirectX 12 compute shaders with no extra work needed. Now, I also mentioned that ComputeSharp has multiple backends. So you might wonder, what about D2D1? So again, it supports both DirectX 12 compute shaders and D2D1 pixel shaders. So D2D1 pixel shaders have a very different architecture respectively with compute shaders, and they also need a very different setup in order to be used. So let's look at what one of these shaders actually looks like and how it's different. So here we can see a pixelation effect. In fact, this is the actual shader that Paint.net uses whenever you apply the pixelation effect in Paint.net. And so if you look at the code here, you can see that first we have a bunch of annotations. So this shader is declaring that it has a single input. You can see that D2D input count attribute. It's also declaring that the input is of complex type, meaning that each output pixel can sample from a given area in the corresponding input. So there's no one-to-one mapping between input and output. Then it's also declaring that each shader invocation can access the current dispatch position within the output grid. And again, all of these annotations are really, really similar to what you would actually write in HLSL code. And this is done for two reasons. First is just to keep the whole experience consistent. And second is also to make things easier if you are already familiar with HLSL and want to migrate and switch to C# instead. And then if we look at the actual shader code, we can see that once again, we have some projections for HLSL. So those would be these float2 and float4 vector types. We have some HLSL intrinsic APIs. So we have these floor and min methods being called. And now we also have some D2D intrinsic APIs. So you can see there's this D2D get scene position and D2D sample input at position. And now if we look at the generated HLSL shader for this shader type, you can see how all of these intrinsics and all of these annotations closely match to the actual D2D1 pixel shader that actually can be compiled and run on the GPU. And so you can see how ComputeSharp takes care of rewriting all of these annotations and all of the intrinsics to be a real D2D1 pixel shader behind the scenes. Now, this is just a very small part of the D2D source generator in ComputeSharp, but there's a lot of additional methods that are also needed. And they're also part of the infrastructure that's required in order to get to running a real D2D pixel shader into an effect that you can use. And that's kind of similar to how it works with DirectX 12 compute shaders. Now, the point that I want to drive home here is just that there's a lot of work here, both with DirectX 12 and D2D1, that you would normally have to take care of yourself for everything. But instead, here you can just rely on ComputeSharp on doing all of this heavy lifting for you behind the scenes. Now, I hope this got you interested in the project, but this was actually just a very small part of what ComputeSharp can do. There are a lot more features that I just couldn't cover here, and there's also a lot more features that I'm planning on implementing in the near future. So just to give you an idea, I'm currently working on extending ComputeSharp D2D1, which is the version of ComputeSharp specifically for D2D1 pixel shaders. That's also the one that Paint.net uses. And I want to add more options to customize effects, and specifically to make the whole system of adding custom draw transform mappings more customizable. Then I'm also working with the Win2D team to add support for custom effects. And in fact, I'm currently working on a PR to add support for this in Win2D. And then once that's done, I also plan on using all of this support to write 2 new packages, which would be the ComputeSharp D2D UWP and WinUI, which will then leverage all of this additional support in Win2D to let you write your own D2D pixel shaders using ComputeSharp, and then easily plug them into your UWP or WinUI3 application through Win2D. Now, all of this work is publicly tracked on the GitHub repo, so you're more than welcome to try any of these features out, leave feedbacks, ideas, or ask questions, and just overall get involved with the project. Thank you so much for your time.
Well,
I'm back to you, Lila.
I'm back. Thank you so much. That was really fascinating to see.
Thanks.
Really complex. I've only done things actually in a game engine, and that, like, shaders, I know just blow mine. So that was really interesting to see all the stuff that you've been doing. So we do have some questions. The
Awesome.
first is from FieldSnable, and he is a shader guru. He's always creating shaders and things. And he wants to know, does it cross-compile to GLSL?
Yeah, that's a question that I get quite often. It actually doesn't. Yeah, basically, I had to make a choice, and that was between trying to somehow abstract over different backends across multiple platforms, or to just double down on Windows, which is what eventually ended up doing, which it's a trade-off, basically. Like, on the plus side, I can now also support D2D, which made like all of the integration with Paint.net possible. On the other side, I cannot cross-compile or like target Vulkan, say, but it's choices, and it's hard.
It always is choices. And I have a couple of other questions, and we've got some time, which is great. So the next one, is there any GPU feature or instruction set that needs to be present to run ComputeSharp?
Yes. So ComputeSharp currently targets Compute Shaders 6.0 for the DirectX 12 backend, and the D2D1 backend instead targets, I think, 5.0. So that pretty much works anywhere. Whereas I guess it's also the same for the DirectX 12 backend, since 6.0 is quite widespread at this point. But also, in case you try to run this code on a device that doesn't have an available physical device that has this, it will automatically falls back to using the work device, which is basically the software adapter that's built into Windows. So what this means is that you can basically run this everywhere. And in fact, I have my whole suite of unit tests that can even run on GitHub Actions, like on the VM, which doesn't even have a GPU. It just uses Warp, and it works just fine everywhere, pretty much.
Awesome. All right, we've got more. All right, so let's see. The next one is, can we use ComputeSharp with web tech, such as Blazor, for 3D rendering on the web?
I'll be honest, that's not something I've personally looked into, and I'm not entirely sure how this could work. I mean, at the end of the day, to actually render stuff with ComputeSharp, you have to, for the DirectX 12 part at least, you need to be able to host a DirectX 12 swap chain panel. So for instance, you can use that in a Win2D application, even a Win32 application, or a UWP one, and so on. I'm not entirely sure that would work in a web application, though I haven't tried myself.
Well, FieldSnable says that then you would need the cross-compiling. So maybe that is. All right, and the next question was a similar thing. Is it compatible with WPF, Uno platform, Avalonia UI, and Blazor? So is that, that's kind of along the same lines.
Right.
But,
all right.
yeah.
So just to go over the general list of frameworks. So this can work. So there's basically 2 components, right? So actually 3. There's the DirectX 12 swap chain panel. There's just doing computations with the DirectX 12 backend, and then there's D2D1 effects. So the swap chain panel can work either in a Win32 application or on UWP and WinUI 3. I'm pretty sure it can work on Avalonia as well if you can host just your native swap chain control. As far as the swap chain panel, I think that doesn't work on WPF because that doesn't support DirectX 12, but that only means that you cannot draw the swap chain directly, but you can still use ComputeSharp for doing all the computations that you want. And this is just for the DirectX 12 part. For the D2D1 part, you can use that pretty much everywhere. Like on WinForms, it also supports D2D1 and WPF supports it as well. So there's a lot of different frameworks where you can fit at least pieces of this project in, depending on your needs. And if you have like a specific use case in mind, please just open an issue and I'll be happy to look into it.
Okay, and the very last question is, do you plan to use OpenGL for ComputeSharp?
I don't. So if I wanted to look into cross-platform solution, I would probably look into Vulkan more than OpenGL, especially because it's more similar to DirectX 12 in a way. But mostly what I ended up doing is just doubling down on native Windows technology. So like I've gone in the opposite direction. So like which is also why I've added the D2D1 support. So yeah, I don't think OpenGL is on the roadmap, unfortunately.
Well, we are at time. There are still more questions coming in. That's a very, very popular topic
awesome.
there. It was fascinating to see. Thank you so much for sharing.
Yeah.
And Sergio, just enjoy the rest of your day and thank you for sharing your knowledge.
Thanks. Same. Have a good rest of .NET Conf.
All right. Cheerio. Bye.
Bye.